This lesson will focus on the takeoff climb requirements for Class A aeroplanes in the commercial transport category. The takeoff climb or takeoff flight path extends from 35 feet above the takeoff surface to 1,500 feet above the takeoff surface. However, with a contaminated runway takeoff, the takeoff climb begins at 15 feet and not 35 feet. The point on the ground directly below the 35-foot screen is called reference zero. There are two main requirements that must be met within the takeoff climb, and these requirements are based upon an engine failure occurring at VEF. Remember that performance of Class A aeroplanes must account for engine failure in all flight phases. The first requirement is that the aeroplane must be able to achieve the minimum climb gradients, and secondly, the aeroplane must be able to maintain sufficient obstacle clearance. Remember that the climb gradient requirements are air-based gradients, and the obstacle clearance requirements use ground-based gradients. When assessing compliance with the regulations, the manufacturer or operator may either use a continuous demonstrated takeoff climb or a segmented takeoff climb. Segmenting the takeoff climb does make the requirements and the procedure a little easier to comprehend. Therefore, we will use a segmented takeoff climb profile, as do most operators and manufacturers. The takeoff climb is generally split into 4 unique segments. Each segment is characteristic of a distinct change in aeroplane configuration, speed, and/or thrust, with various actions and climb gradient requirements. Generally, there are 4 segments, and you will need to learn what unique characteristics define each segment. The takeoff flight path starts once the takeoff is complete. In other words, at 35 feet, with the aeroplane at V2 with one engine inoperative. The 35-foot screen marks the start point of segment 1. The objective at this point is to climb as expeditiously as possible, which is difficult because of the lack of excess thrust, due to the large amount of drag created by the gear and flaps, and the fact that only one engine is in operation. Therefore, the strategy is to retract the gear and flaps as soon as possible. Since retracting flaps at low speeds close to the ground is dangerous, the only option is to retract the gear. Once the gear is up and locked, then the first segment is finished. During this segment, the steady gradient of climb must be positive. The second segment starts at the end of the first segment. That is, when the gear is up. The objective now is to retract the flaps. However, flap retraction is not permitted below 400 feet. Therefore, the action by the pilot is simply to climb, and no less than V2, until 400 feet is reached. Once 400 feet is reached and flap retract can commence, segment 2 ends. Since the aeroplane has had the main source of drag removed, the minimum gradient requirement is more severe at no less than 2.4%. Segment 3 starts above 400 feet and is the flap retraction and acceleration segment. However, retracting the flaps will increase the stall speed. This reduces the aeroplane's safety margin. Therefore, the aeroplane must accelerate during flap retraction from V2 to the 0 flap speed and then to the final takeoff speed. The final takeoff speed is also called the final segment speed and is intended to be the one engine inoperative best angle of climb speed. Once this has happened, thrust can be reduced from maximum takeoff thrust, TOGA, to maximum continuous thrust, MCT. In fact, maximum takeoff thrust is limited to only 10 minutes. Therefore, acceleration and flap retraction must be complete by then. The acceleration phase of this segment poses a climb problem. To climb, excess thrust is needed. However, accelerating the aeroplane also requires excess thrust. Therefore, it is not possible to adequately accelerate and climb at the same time, and as such, segment 3 can be flown level, as shown by the illustration. Although there is no climb gradient required in segment 3, the authorities have to quantify the amount of minimum performance the aeroplane is required to produce. So, if the aeroplane was not accelerating, it would be able to achieve a minimum gradient of 1.2%. The fourth segment starts when the flaps are retracted, the final segment speed is achieved, and the thrust is set to maximum continuous thrust. From this point, the aeroplane is climbed to above 1,500 feet, where the takeoff flight path ends. The pilot will either rejoin the airfield to land or continue en route to the takeoff alternate. The climb gradient for this last stage must not be less than 1.2%. One last point. The gradient requirements for Class A aeroplanes with more than 2 engines forms part of the syllabus, and therefore they need to be remembered as well. Although we have already mentioned it in the previous lesson, the climb limit mass tells us what the maximum mass of the aeroplane can be in order to achieve the minimum gradient requirements. Having a mass greater than the climb limit mass would mean that the aeroplane will not have sufficient performance in the event of engine failure to achieve the climb gradient requirements. The graph to calculate the climb limit mass is on page 11 of section 4 in CAP 698. We have worked through an example in the previous lesson, but nonetheless, ensure you're confident in being able to use this graph. The introduction to the climb section, shown on the previous page, reiterates the climb requirements, and it states that during the takeoff climb, the aeroplane must A. Attain the most severe gradient requirement of the takeoff net flight path, and B. Avoid all obstacles in the obstacle accountability area by the statutory minimum vertical interval. Both of these requirements have already been mentioned in the introduction section of this lesson. The climb limit mass deals with point A. In other words, being at or below the climb limit mass guarantees attainment of the most severe gradient requirement of the takeoff flight path. What is the most severe angle of the takeoff flight path? Well, shown on screen is the takeoff flight path and segments of the takeoff climb. The most severe gradient requirement is in segment 2, which for a twin-engine jet aeroplane is 2.4%. Therefore, the climb limit mass ensures that the aeroplane, in the event of engine failure, is able to attain a 2.4% gradient or more. Remember that these climb gradients are air-based and therefore independent to the effect of wind. Looking through the climb limit mass graph confirms this, since there is no account for wind. Having discussed the minimum climb gradient requirements and how to ensure the aeroplane attains them, we need to focus on the obstacle clearance requirements. In EU OPS 1, it states that an operator must ensure that the net takeoff flight path must clear all obstacles by a vertical margin of at least 35 feet. If the aeroplane is unable to do so, it must turn away from the obstacle and clear it by a horizontal distance of at least 90 meters plus 0.125 times d, where d is the horizontal distance the aeroplane has travelled from the end of the takeoff distance available. For aeroplanes with a wingspan of less than 60 meters, a horizontal obstacle clearance of half the aeroplane wingspan plus 60 meters plus 0.125 times d may be used. However, obstacles further away than the values in the table need not be considered. We have seen this horizontal clearance information before when we were discussing Class B multi-engine obstacle clearance. However, there are two crucial points to consider when trying to work out the vertical clearance. The first relates to climb gradient, which, if you remember, is a ground-based gradient. In order to work out the obstacle clearance of the aeroplane, the climb gradient needs to be known. But EU OPS 1 states that the climb gradient to use for the purpose of calculating obstacle clearance must be the net climb gradient. Remember that the net gradient is the gross gradient diminished by a safety factor. In this case, the safety factor changes depending on the number of engines. In the case of two-engine aeroplanes, the net gradient is the gross gradient decreased by 0.8%. For three-engine aeroplanes, the net gradient is the gross gradient decreased by 0.9%. And for four-engine aeroplanes, the climb gradient must be made worse by 1%. Using the net gradient instead of the gross gradient in the takeoff flight path will produce the net takeoff flight path as shown on screen. As we stated at the beginning, the net takeoff flight path must clear all obstacles by 35 feet. The second point to consider is the effect of wind on the ground gradient. Headwind will increase the ground gradient and improve obstacle clearance, whereas tailwinds will decrease the ground gradient and deteriorate the obstacle clearance. EU OPS 1 states that when adjusting for wind to calculate the ground gradient, no more than 50% of the reported headwind and no less than 150% of the reported tailwind must be used. Carrying out this rule simply adds another safety margin into the calculation. We stated that if the aeroplane is unable to clear the obstacle vertically, then it can turn away from the obstacle and clear it horizontally. However, there is a restriction on how much the aeroplane is allowed to turn. Clearly, it is not safe if the aeroplane needs to bank sharply to clear the obstacle by the regulatory margins. Turning can increase the effective weight by imposing extra G-loads, and therefore the climb gradient is reduced and stall speeds are increased. Firstly, the aeroplane is not allowed to turn below a height of 50 feet or a height equivalent to half the wingspan. Thereafter, and up to a height of 400 feet, the aeroplane is not banked by more than 15 degrees, and from 400 feet, not banked by more than 25 degrees. EU OPS 1 does permit operators to exceed these bank angles, providing the operator uses special procedures, and that these procedures have been approved by the relevant authority. The special procedures must take account of the gradient loss from such bank angles, and these must be published in the aeroplane flight manual. The maximum bank angles that the special procedures allow is up to 20 degrees between 200 and 400 feet, and up to 30 degrees between 400 and 1500 feet. If any turn of more than 15 degrees is required at any point in the takeoff flight path, then the vertical clearance is increased to 50 feet instead of 35 feet. Manually working out the obstacle clearance capability of the aeroplane could take a long time, since there are so many points to bear in mind, and the calculation itself is quite lengthy. To remind you of the complexity of these calculations, you may remember this image from the multi-engine Class B requirements. Just bear in mind, for Class A aeroplanes, it's even more complicated than this. Thankfully, most operators and manufacturers have produced either rapid lookup tables or graphs to quickly enable the pilot to work out if an obstacle in the takeoff climb will be cleared by the relevant vertical margins following engine failure. These tables or graphs will produce a mass. This mass is called the obstacle limit mass. It is the maximum mass that will allow the aeroplane, in the event of engine failure, to clear the obstacle by the relevant vertical margin. The obstacle limit mass graph shown on screen is found in CAP 698 on page 36 of section 4. We have already worked through this graph in the previous lesson. Notice that winds are included in the graph. This is important because obstacle clearance calculations must use ground gradients, and these are dependent on wind. In fact, remember that EU OPS 1 had a rule about the wind. It stated that when using the winds to work out the ground gradient, only use 50% of headwinds and no less than 150% of tailwinds. Notice the slope of the headwind and tailwind lines. This shows that the graph applies the wind rule for you. Therefore, if you enter the graph with the actual reported wind, the graph corrects it automatically, so you don't need to. Once the details of the obstacle have been entered, as shown by the example, the obstacle limit mass can be read off. And in this case, the obstacle limit mass is 51,700 kilograms. Taking off with a higher mass than this would not ensure adequate vertical clearance. However, if this mass unduly restricts the takeoff mass, then the aeroplane may be dispatched with a greater mass, so long as the aeroplane turns around the obstacle, clearing it by the relevant horizontal margins, and does not exceed the turn restrictions when trying to do so. There is only a remote or very remote chance that an engine will fail on takeoff, and therefore meeting the climb gradient and obstacle clearance requirements will not be a significant concern. However, there is one more requirement that plays a role in normal operations. As aeroplane traffic increases, there will be increasing concerns about the effect of the traffic on local communities. Therefore, most airfields near urban areas enforce some sort of noise abatement requirements. There are two such procedures. The first procedure, Noise Abatement Departure Procedure 1, is intended to provide noise reduction for noise-sensitive areas in close proximity to the departure end of the runway. The second procedure, Noise Abatement Departure Procedure 2, provides noise reduction to areas more distant from the runway end. Noise Abatement Departure Procedure 1 involves initially climbing to 800 feet above aerodrome level at no less than V2 plus 10 knots. On reaching 800 feet, adjust and then maintain engine power in accordance with the noise abatement schedule in the aircraft operating manual, and maintain a climb speed of V2 plus 10 to 20 knots with flaps and slats still in the takeoff configuration until a maximum of 3,000 feet. From 3,000 feet, and while maintaining a positive rate of climb, accelerate to en route climb speed, retracting flaps and slats on schedule. Noise Abatement Departure Procedure 2 involves initially climbing to 800 feet at no less than V2 plus 10 to 20 knots. On reaching 800 feet above aerodrome level, decrease aircraft pitch, and whilst maintaining a positive rate of climb, accelerate towards zero flap speed, VZF, and reduce power with the initiation of the first flap or slat retraction. Alternatively, when the flaps and slats are retracted after 800 feet, then reduce thrust and climb at VZF plus 10 to 20 knots up to 3,000 feet. On reaching 900 meters, 3,000 feet, above aerodrome level, transition to normal en route climb speed. Noise abatement procedures in the form of reduced power takeoff should not be required in adverse operating conditions, such as contaminated runways, poor visibility, high crosswinds, wind shear, and thunderstorm activity. This completes the climb requirements for Class A aeroplanes. Focus on understanding and learning the segments for the takeoff climb. Knowing when each segment starts and stops, and what happens in each segment, forms a vital part of the ATPL performance exam. Ensure you can also accurately work through the climb performance graphs in CAP 698. Lastly, make sure you can detail the difference between the two noise abatement procedures. Don't forget, once you start your job with the airline, you will go through type training and line training. This will involve studying in a lot more detail the performance and procedures of the aeroplane you will fly, so that by the time you take your first passengers, you will feel a lot more comfortable with how the whole process works. The en route phase of flight starts at 1,500 feet above the departure aerodrome and ends once the aeroplane has reached 1,500 feet above the intended destination aerodrome. Similarly, with other phases of flight for Class A aeroplanes, the en route regulations account for engine failure. Therefore, manufacturers and operators of Class A aeroplanes must ensure that the performance of the aeroplane subsequent to engine failure is still able to meet the regulations. Generally, once the en route phase of flight commences, the pilot workload is reduced. The autopilot and auto-thrust systems are usually engaged, and this relieves the pilots from basic flight manoeuvring, allowing them to concentrate on other things. Therefore, during the en route phase, most pilots carry out in-flight monitoring, flight performance data checks, and review emergency procedures. Despite the relatively light workload for the pilots during the en route flight phase, there is a lot of information that you need to understand about this phase of flight. Firstly, we will discuss the climb to the en route altitude. Then we will detail the en route altitudes and how they are calculated, as well as discussing various flight speeds. Lastly, we will detail the descent, both normal descent and the descent forced by either engine failure or depressurization. After a normal takeoff, climbing to the en route altitude is a straightforward affair. Once the aeroplane configuration is clean, a set climb profile or climb schedule will be flown. Initially, the aeroplane climbs at a constant indicated airspeed. However, continuously climbing at a constant indicated airspeed causes the Mach number to rise. Beyond a certain altitude, the Mach number gets too high, and serious aerodynamic forces start to affect the aeroplane. In the 737 family, the maximum Mach number, MMO, is 0.82. Therefore, at some lower altitude, the aeroplane needs to change its climb profile to a constant Mach number climb. The altitude at which this change occurs is called the crossover or changeover altitude. In brief summary then, the climb profile involves the aeroplane initially climbing at a constant indicated airspeed, and then at the crossover altitude, the aeroplane then climbs at a constant Mach number. However, ICAO limits the maximum indicated airspeed to 250 knots below 10,000 feet. This slightly changes the climb profile. For the majority of the 737 family, the climb profile is 250 knots indicated airspeed up to 10,000 feet. Then the aeroplane is accelerated to 280 knots and the climb continued at this speed. When the Mach number reaches 0.74, as shown here, the aeroplane maintains a climb speed of 0.74 Mach until the en route cruise altitude. Notice in this case, the crossover altitude is at about 31,000 feet. However, you need to understand what happens to the crossover altitude if a faster indicated airspeed climb is maintained. And for this example, we'll increase the second part of the indicated airspeed climb from 280 to 325 knots. Initially, the aeroplane will still climb at 250 knots, but once reaching 10,000 feet, the aeroplane will be accelerated to 325 knots, and then climb at 325 knots. Once the Mach number has increased to 0.74, then the aeroplane climbs at 0.74. Notice now the crossover altitude is lower at 18,000 feet. Therefore, if the indicated airspeed is increased in the climb profile, the crossover point decreases to a lower altitude. Before we proceed to the en route altitude, it is important at this point to briefly detail a few important speeds, most of which you have already covered. These speeds are commonly expressed as Mach numbers. The first of these speeds is the maximum operating speed, either called VMO when using indicated airspeed, or MMO when using Mach numbers. For the majority of the 737 family, VMO is 340 knots, and MMO is 0.82. Flying beyond these speeds in a commercial operational context is not permitted, and may cause either structural damage or a high-speed stall. The next two speeds are used in reference to describing the range of the aeroplane, and were mentioned in the en route lesson of the General Performance Principles section. These two speeds are the Maximum Range Cruise Speed, MRC, and Long Range Cruise Speed, LRC. When these speeds are referenced in terms of a Mach number, the abbreviation is changed to MMR and MLRC, respectively. As you can see from the graph plotting cost and speed, the advantage of flying at the maximum range speed is simply that the aeroplane will use the least amount of fuel and therefore have the least fuel cost for a given distance. However, operationally, the faster long-range cruise is used. The simple reason why this speed is used is because by getting to a destination more quickly, more revenue-earning flights can be carried out in any given period. In other words, over a given time period, 4% more flights can be carried out, with only a fuel consumption increase of 1%. The long-range cruise speed does suffer from limitations. It doesn't take into account the variable cost of fuel from day to day or month to month, and neither does it account for the operational costs. When fuel prices are high, the extra fuel consumption may dramatically increase the overall cost of the flight, and a more operationally economical speed may need to be flown. The relationship of these costs is explained by the use of a cost index, and the speed flown based upon the cost index is called econ. This will be discussed next. The fundamental rationale of the cost index concept is to achieve minimum operation trip cost by means of a trade-off between time-related costs and fuel-related costs. The cost index is used to take into account the relationship between fuel and time-related costs. With time-related costs, the faster the aircraft is flown, the more money is saved in time costs. This is because the faster the aircraft is flown, the more miles can be flown for time-related components. It also means that more miles can be flown between inspections when considering maintenance costs. Notice that these costs are minimum at the maximum operating speed. However, if the aircraft is flown faster, the fuel burn increases, and total fuel cost for the trip increases. Fuel costs will be minimum at the maximum range speed, and maximum at the maximum operating speed. Adding the time-related costs and fuel-related costs together produces a direct operating cost, or more simplistically, a total operating cost. The flight management system uses the time and fuel-related costs to help select the best speed to fly. You can see from the total cost curve that the speed which gives the minimum total operating cost is the most economical speed to fly. This speed is called econ. In other words, the minimum cost speed. The value of the econ speed is worked out by the flight management system, based upon the value of the cost index. As a formula, the cost index is a ratio of cost of time, CT, divided by the cost of fuel, CF. When fuel costs are high and time costs are very low, then the cost index is almost zero. With a cost index of 0, the econ speed is at the maximum range speed. When time costs are high and fuel costs are low, then the cost index is very high, and the econ speed will be closer to the maximum operating speed, so that the massive time costs are reduced. To summarize then, increasing the cost index from 0 to maximum will increase the econ speed from the maximum range speed to VMO. For most aeroplanes, the cost index varies from 0 to 99, or from 0 to 999. Once the aeroplane has completed the climb profile and has reached the top of the climb, the aeroplane will level off at the appropriate altitude. This cruise altitude should ideally coincide with optimum altitude. You may recall that the optimum altitude was the altitude for maximum specific range, or maximum fuel mileage. As a general rule, this altitude is not constant. As weight decreases during the flight from fuel consumption, the optimum altitude increases, as illustrated in the graph. Therefore, to constantly fly at the optimum altitude, the aeroplane will not actually fly level, but will in fact slowly be climbing in the cruise. On the other hand, ATC restrictions require level flight crews to ensure vertical separation with other aeroplanes. Aircraft must fly by segments of constant altitude, which must be as close as possible to the optimum altitude. The level segments are established within 2,000 feet of the optimum altitude. Remaining within 2,000 feet of the optimum altitude ensures the range is 99% of the maximum specific range. There may be several step climbs during the flight, and the aeroplane will be gaining altitude throughout this process. However, there is a limit on how high the aeroplane is permitted to operate and able to operate. As the aeroplane altitude increases, the thrust that is required to maintain a given speed increases. Eventually, there will be an altitude where the thrust is increased to its maximum cruise value, and it would not be possible to climb any higher without exceeding the thrust limits. This altitude is called the maximum altitude, and is shown on the illustration. However, the hotter the atmosphere, the lower this altitude becomes, and in exceptionally hot atmospheres, the maximum altitude is almost the same as the optimum altitude. Although the aeroplane cannot operate above the maximum altitude, there are other altitude limits placed upon the aeroplane. Before we can discuss the other limits on the operating altitude of an aeroplane, it is important to discuss aeroplane stalling. When the speed of the aeroplane is reduced, in order to still produce enough lift to balance weight, the angle of attack must increase. However, below a certain speed, the angle of attack on the wings is such that the flow of air over the wing starts to separate from the boundary layer, producing turbulent airflow. The separation point fluctuates back and forth along the wing, making strong eddies in the turbulent airflow. These strong eddies buffet the elevators or tailplane. This phenomenon is called the low-speed buffet. Flying below this speed will dramatically decrease the lift, and a full stall ensues. For a given weight and configuration, the aeroplane will always stall at the same indicated airspeed. But the equivalent Mach number for the low-speed buffet and stall increases with altitude, as illustrated in this simplistic graph. The Mach number for the low-speed buffet is abbreviated to m-min. A similar buffet can occur at high speed. At very high speeds, close to the speed of sound, the compressibility of the air ahead of the aeroplane leads to the formation of shock waves or high-pressure waves. These shock waves create a disturbance to the flow of air over the wing, causing it to separate and create turbulent eddies. Similarly to the low-speed buffet, these eddies will buffet the elevator. This phenomenon is called the high-speed buffet, and the Mach number for the high-speed buffet decreases with altitude. Flying faster than this speed may cause a high-speed shock stall in an aeroplane whose wings are not designed to overcome such effects. The Mach number for the high-speed buffet decreases with altitude, as shown. This speed is commonly abbreviated to m-max. Taking into consideration the Mach number for both low-speed and high-speed buffet, it means that there are two Mach numbers below and above which the aeroplane is unable to fly. This speed range between the Mach number for the low-speed buffet and high-speed buffet is called the buffet margin. The important point to understand is that the margin between the low-speed and high-speed buffet decreases with altitude. Notice that at this altitude, the low-speed and high-speed buffets are coincident. It is impossible to fly higher than this altitude. Flying slower or faster than the speed shown will stall the aeroplane. In fact, even maneuvering the aeroplane will initiate a stall, because maneuvering the aeroplane will increase the effective weight and increase the stall speed. This altitude is called the aerodynamic ceiling, or coffin corner. To prevent aeroplanes from operating too close to this altitude, an operational limit is set below this point. Notice that a 1.3 G maneuver moves the buffet speed lines to this position. Notice that now the Mach number for the low-speed and high-speed buffet are coincident at a lower altitude. This altitude is called the 1.3 G buffet limit altitude or maneuver ceiling, and is usually about 4,000 to 6,000 feet below the aerodynamic ceiling. Adding these two altitudes onto the graph shown earlier helps you to see how these different altitudes and ceilings relate to each other. When the aeroplane gets close to the destination airfield, it will reach a point which marks the beginning of the descent. This is called the top of descent. You may remember that in order to initiate a descent, firstly the thrust must be reduced, and then the nose is lowered to get weight to act forwards to balance the drag. The balance of forces ensures a constant speed can be maintained during the descent. The descent profile is almost the reverse of the climb profile. The climb for a typical 737 is initially flown at 250 knots. Then, at 10,000 feet, this changes to 280 knots. And then at the crossover altitude, Mach 0.74 is maintained. The descent is flown initially at 0.74 Mach. Then, at the crossover altitude, the speed is kept constant at 280 knots. But when 10,000 feet is reached, no more than 250 knots must be flown. Shown on screen are the characteristics of that descent, so you can see what happens to the gradient and rate of descent throughout the descent profile. If at any point air traffic control asks the pilots to expedite the descent, then the only action by the pilots would be to deploy the speed brakes. This increases the drag, which must be balanced by more weight apparent thrust. Therefore, the nose is lowered, which increases both the angle and rate of descent as per the instruction of air traffic control. The next descent to consider is the descent characteristic following either depressurization or engine failure. In flight, engine or pressurization failures are potential problems. They seriously impact on flight altitudes and therefore become very constraining over mountainous areas. In the case of an engine failure during flight, the remaining thrust is no longer sufficient to balance the drag force, and therefore the cruise speed cannot be maintained. The only solution is to descend to a lower flight altitude, where the remaining engine can provide enough thrust to balance the drag and allow level flight once more. To achieve this, the aeroplane is allowed to decelerate from the selected cruise speed to the velocity of minimum drag. Then the nose is lowered to get weight apparent thrust to balance drag. As the aeroplane descends into the lower atmosphere, where density is greater, the remaining engine can develop more thrust, which will mean that weight apparent thrust can be slowly reduced until an altitude is reached where the remaining engine generates enough thrust to balance drag. At this altitude, the aeroplane can level off, as shown. This procedure is called the drift down, and it produces a drift down profile, such as the one shown on screen. In fact, the profile on screen is the gross drift down flight path. This path must, of course, be above all relevant obstacles, but this will be discussed later. With a pressurization failure, the procedure is a little different. At high altitude, following depressurization, the air in the cabin escapes, and very quickly the cabin air becomes the same air as outside. At high altitude, the problem is that there is very little oxygen to breathe. Therefore, oxygen must be carried on board and supplied to crew and passengers through oxygen masks. However, the amount of oxygen carried is limited. Therefore, the aeroplane must descend as rapidly as possible to 10,000 feet, where there is sufficient oxygen before the oxygen supply runs out. The procedure involves configuring the aeroplane for the maximum rate of descent. You may recall from the descent lesson in the General Performance Principles section that in order to achieve a maximum rate of descent, excess power required has to be as large as possible. Therefore, drag must be high and speed must be high. As a result, the first actions of the pilot are to don the oxygen masks, initiate descent, close the throttles, apply the speed brakes, and then allow the aeroplane to accelerate to maximum operating speed, which is either VMO or MMO. This configuration is then maintained until at least 10,000 feet, where there is sufficient oxygen to breathe. One of the crucial points about the drift-down procedure is the clearance of obstacles. Because the aeroplane is forced to descend, terrain, like mountains, may present a flight hazard. When assessing the terrain hazard, a safety margin must be introduced. When planning routes and planning the flight profile, it is not the gross flight profile that must be assumed, but rather the net flight profile. In other words, the flight profile must be made worse by a safety factor. This safety factor is based on assuming a gradient of descent that is worse than the aeroplane can actually achieve. For two-engine aeroplanes, with one engine inoperative, the gross gradient of descent is increased by 1.1%. This increases to 1.4% for 3-engine aeroplanes and 1.6% for 4-engine aeroplanes. OPS 1 details the regulations for en route obstacle clearance. It states that the gradient of the net flight path must be positive at least 1,000 feet above all terrain and obstructions along the route, within 5 nautical miles on either side of the intended track. This regulation is essentially saying that the aeroplane must be able to demonstrate that it can level off and achieve a positive climb at 1,000 feet above all obstacles along the route. This may be very difficult to achieve if there was a very high mountain around. If the aeroplane is unable to have a positive climb 1,000 feet above all obstacles, then the aeroplane may level off at a lower altitude, so long as any obstacle encountered in the descent is cleared vertically by at least 2,000 feet. In order to find out if the aeroplane is able to level off at 1,000 feet above an obstacle, then use the graph in Cap 698 on page 40 of Section 4. Simply enter the graph with the level off altitude that is required, and the graph will show the mass that the aeroplane will need to be at in order to level off at that altitude. In the example, in order to level off at 18,000 feet, the aeroplane would need to have a mass of just under 48,000 kilograms. If this is not possible, then other graphs, shown on page 41 to 44 of Cap 698, must be used. These graphs are more complicated, but importantly, these graphs will enable the pilot to work out if the aeroplane can clear any obstacle in the flight path by 2,000 feet. When you use the graph, be careful to adjust the weight of the aeroplane for any non-standard conditions and anti-ice use. Notice that the heavier the aeroplane, the longer and lower the drift-down procedure is. The last of the regulations states that the aeroplane must have a positive gradient at 1,500 feet above the aerodrome where the landing is assumed to be made after engine failure. After engine failure, the lower operating altitude significantly decreases the engine's efficiency. So much so that the fuel flow on the remaining engine is almost as much as the fuel flow with both engines operating at high altitude. This fact, together with the reduced true airspeed, means that the specific range is dramatically decreased. As a result of the reduced range, it is now not possible to reach the destination airfield. And in fact, the priority now is to find an alternate airfield to land before the fuel runs out. This issue is of such importance that it was necessary to regulate it. The authorities have set a safety standard that in the event of engine failure, the aeroplane must have the capability of reaching a suitable airfield within a certain time period. EU OPS 1 states that twin-engine aeroplanes beyond a certain size must be no further away from a suitable aerodrome than the distance flown in 60 minutes using the one engine in operative cruise speed. For aeroplanes with 3 or more engines, the time is increased to 90 minutes. Therefore, at all points on the route, a twin-engine aeroplane must be within 60 minutes of an alternate airfield. This regulation has a significant impact on flight routes, especially over the sea. In the example on screen, you can see that a direct track to North America from Europe is not possible. However, as more and more reliable and efficient aeroplanes are produced, an extension to the 60-minute rule has been introduced. This extension is called ETOPS, and it stands for Extended Range with Twin-Engine Aircraft Operations. It hugely increases the operational capability of twin-engine aeroplanes, where only 3 or more engine aeroplanes could operate. However, ETOPS must be applied for by the airlines concerned, and approval gained from the appropriate aviation authority. To gain ETOPS approval, a greater range of performance parameters must be known, and these accompany the application, and are eventually published in the operating manual. Gaining an ETOPS approval of 120 minutes, for example, will greatly benefit flight tracks across the Atlantic Ocean, as shown. The route from Paris to New York, for example, can now be flown direct by a twin-jet aeroplane. Currently, the longest ETOPS approval is given to the Boeing 777. It currently holds an approval of 180 minutes, with contingencies for 207 minutes over the Pacific. In the future, ETOPS may be evolving into a newer system called LROPS. LROPS stands for Long Range Operational Performance Standards, which will affect all aircraft, not just those with twin-engine configuration. This completes the lesson on the en route and descent phases of flight for Class A aeroplanes. Concentrate on the climb profile and ensure you understand what happens to the profile when different speeds are selected. Also ensure you understand optimum altitude, and specifically on how to operate the aeroplane close to this altitude. Remember the limitation of the aerodynamic and maneuver ceilings, and ensure you never approach these altitudes. Be careful not to exceed the operating limits placed on the aeroplane by the operator or manufacturer. If you do, you are exposing yourself, the aeroplane and its passengers, to an untested and unaccountable flight regime. Lastly, know your aeroplane's capabilities by looking periodically through the performance data in the operating manual. Knowledge of the aeroplane and where to find the performance information greatly enhances the decisions in an emergency. This is the last lesson in the Class A performance section. The lesson will focus on the Class A performance requirements for the landing stage of flight. There are two main regulation requirements. The first requirement is that the landing distance must not exceed the landing distance available. In other words, the aeroplane must be able to land within the length of the runway. This requirement can be called the landing distance requirement. Remember that the landing starts at the 50 feet landing screen and ends once the aeroplane has reached a full stop. Don't forget that the target speed to be attained at the screen height is called VREF, which you may recall for a Class A aeroplane must be no less than 1.23 VSRO and no less than VMCL. The second requirement is that should the aeroplane be unable to land, it must be able to climb away from the aerodrome with an adequate climb gradient. This latter requirement can be called the landing climb requirement. We will deal with the climb gradient requirements first. The climb gradient requirements are a little complicated and are spread through both EU OPS 1 and CS25. Assimilating both these documents allows the landing climb gradient requirements to be split into two parts. The two parts are based on either all engines operating or with one engine inoperative. The all engines operating landing climb requirement is sometimes called the landing climb. This requirement is intended to guarantee adequate performance to arrest the descent and allow a go-around from the final stage of a landing. The regulations state that the steady gradient of climb may not be less than 3.2% with both engines operating, but only using the amount of thrust that is available after 8 seconds on initiation of go-around power. The speed used in the climb cannot be less than 1.23 VSRO and a speed not less than VMCL. The second part of the climb requirement is based on one engine being inoperative and is sometimes called the approach climb. This requirement is intended to guarantee adequate performance in the go-around configuration after an approach with an inoperative engine. The regulations state that the steady gradient of climb may not be less than 2.1% with the critical engine inoperative and the remaining engine at go-around power. The mass is assumed to be maximum landing mass, and the speed used in the climb cannot be more than 1.4 VSR. Lastly, the landing gear is assumed to be retracted. However, the approach climb gradient requirement does change. For 3-engine aeroplanes, the gradient must not be less than 2.4%. And for 4-engine aeroplanes, the gradient must not be less than 2.7%. Note that the gradient requirements stipulated here are all air gradients, and therefore are independent of wind. EU OPS 1 more precisely describes the climb requirements by stating that the landing mass of the aeroplane must be such that the climb gradient requirements can be met. The maximum mass that the aeroplane can have and still meet the climb gradient requirements is called the landing climb limit mass, or climb limit landing mass. Exceeding this mass means that the aeroplane will not be able to attain the climb gradient requirements. Shown on page 47 of section 4 in CAP 698 is an example of a graph to calculate the landing climb limit mass. Working through an example, we can assume a temperature of 20 degrees Celsius at a destination airfield pressure altitude of 2,000 feet. The flap setting section here determines how far up the sloping guideline we go. In our example, we'll assume a flap setting of 40 degrees, which means we go straight through the flap section. In this example, the landing climb limit mass is 61,800 kilograms. Remember, exceeding this mass means it would not be possible to meet the climb gradient requirements. Before we complete the study of the graph, ensure you have looked at any correction information. Notice that near the bottom of the page is a long list of corrections that may need to be applied. The graph is based on the air conditioning packs being on automatic. If the air conditioning packs are off, increase the landing climb mass by these amounts, depending on the flap setting. The bottom set of corrections applies to flight in icing conditions and the use of anti-ice equipment. Since this equipment drains thrust from the engines, the landing climb limit mass will need to be corrected. This completes the graph for working out the landing climb limit mass. But remember, not all Class A aeroplanes have graphs that look like this, so be sure to familiarize yourself with the performance data of the aeroplane type you fly. Having discussed the landing climb requirements, let us now turn to the landing distance requirements. EU OPS 1 states that an operator must ensure that the landing mass of the aeroplane allows a full stop landing from 50 feet above the threshold, within 60% of the landing distance available for turbojets, and within 70% of the landing distance available for turboprops. This means that turbopropeller aeroplanes must be able to land within 70% of the landing distance available, but jet aeroplanes must land within 60% of the landing distance available. To help you calculate the relevant distance, use the factor 1.43 for turboprops and 1.67 for turbojets. Let's work through a few examples, so you can become familiar with using them. A turboprop aeroplane has a calculated landing distance of 693 meters. What is the minimum length of landing distance that must be available at the airfield in order to comply with the regulations? In other words, we must work out what 693 meters is 70% of. Therefore, multiply 693 meters by 1.43. This gives an answer of 991 meters. Therefore, if the runway is 991 meters or more, the aeroplane is landing within 70% of it. Let's look at it another way. If the available landing distance was 2,015 meters, then what must be the maximum landing distance of a turboprop in order to comply with the regulations? In this case, we must find out what 70% of 2,015 meters is. Therefore, divide 2,015 meters by 1.43. This gives an answer of 1,409 meters. In this example, a turboprop aeroplane must come to a full stop within 1,409 meters. Let us carry out one more example, but this time using a turbojet aeroplane. Remember, turbojets must land within 60% of the runway, and the factor to use was 1.67. If the calculated landing distance is 857 meters, what is the minimum length of landing distance available? For this example, multiply 857 by 1.67. This gives an answer of 1,431 meters. Therefore, the landing distance available must be more than 1,431 meters long. These examples are important, since questions like this form part of the aircraft performance exam. Try not to get confused about when to multiply or divide by the factor. In complying with the landing requirements, EU OPS 1 states that the operator must take account of the altitude at the aerodrome, not more than 50% of the headwind component, or not less than 150% of the tailwind component, and the operator must account for the runway slope in the direction of landing if greater than plus or minus 2%. An important landing requirement is the one that addresses landing on wet or contaminated runways. EU OPS 1 states that if weather reports or forecasts indicate that the runway at the estimated time of arrival will be wet or contaminated, the landing distance must be at least 115% of the dry landing distance. In other words, on wet or contaminated runways, the landing distance must be increased by 15%, or by a factor of 1.15. However, EU OPS 1 also states that a value of less than 115% may be used if the aeroplane flight manual includes specific information about wet or contaminated runways. Even though the landing distance increases on wet or contaminated runways, the aeroplane must still be able to demonstrate it can stop within 70% of the runway for turboprops and 60% of the runway for turbojets. Therefore, just be sure you understand the implications of this. Let's work through an example. If the dry landing distance of a turbojet aeroplane is 920 meters, what would the minimum landing distance available have to be if the runway is wet? Since the runway is wet, we have to increase the landing distance by 15%. We do this by multiplying 920 meters by a factor of 1.15. Therefore, the wet landing distance is 1,058 meters. EU OPS stated that the landing distance must be within 60% of the landing distance available. Therefore, to find what minimum length of runway is needed, multiply 1,058 by the factor 1.67. This gives an answer of 1,767 meters. Therefore, if the runway is wet and the dry landing distance is 920 meters, then the minimum length of landing distance available at the airfield must be 1,767 meters. In fact, we can simply summarize to say that for jet aeroplanes, the combined wet factor and regulation factor is 1.92, and for the turboprop, this factor is 1.64. One of the last landing requirements is about the dispatch mass, which we have already looked at in previous lessons. The dispatch rules for Class A aeroplanes are found in EU OPS 1.515, paragraph C, and state that for dispatching an aeroplane, it must be assumed that, firstly, the aeroplane will land on the most favourable runway at the destination airfield in still air, and, secondly, that the aeroplane will land on the runway most likely to be assigned, considering the probable wind speed and direction. If the still air requirement cannot be met, the aeroplane may be dispatched only if there are two alternate aerodromes at which full compliance of the regulatory dispatch requirements can be met. These dispatch regulations may sound a little complicated, so let's examine them further. The first assumption is that the aeroplane will land on the most favourable runway, in still air or zero wind. This means that, assuming zero wind at the destination airfield, the runway which would accommodate the largest possible landing mass would be selected, since this is the most favourable runway. In our example on screen, assuming zero wind, runway 04 and runway 22 both allow a maximum landing mass of 51,000 kilograms. But runway 31 and runway 13, being much shorter runways, allow a maximum landing mass of only 43,000 kilograms. Therefore, the most favourable runway in still air is either runway 04 or 22, which both allow a maximum landing mass of 51,000 kilograms. The second dispatch assumption is that the aeroplane will actually land on the most likely runway to be assigned, considering the probable wind speed and direction. In this case, runway 04 has a strong headwind for the landing, which will allow the aeroplane to land at a much greater mass than if there were no wind. In our example, the headwind has increased the maximum landing mass to 52,500 kilograms. However, runway 22 has a tailwind, which will decrease the maximum landing mass to 47,800 kilograms. Runway 31 and runway 13 both have a full crosswind. Therefore, the maximum landing mass for these two runways will be the same as for still air. If the second dispatch assumption is that the aeroplane will land on the runway most likely to be assigned considering the probable wind speed and direction, then it would have to be runway 04, with a maximum landing mass of 52,500 kilograms. In summary then, the first assumption requires that the pilot select runway 04 or 22 for a maximum still air landing mass of 51,000 kilograms, and the second assumption will require the pilot to select runway 04 for a maximum landing mass of 52,500 kilograms. Now we need to consider what to use as the dispatch mass of the aeroplane. If the aeroplane was dispatched at 52,500 kilograms mass, and then on arrival at the airfield, the forecast wind was not experienced and was less than 15 knots, the aeroplane would not be able to land. Therefore, the aeroplane must be dispatched with a mass of 51,000 kilograms. Dispatching the aeroplane with this mass would mean that no matter what wind conditions prevail at the destination airfield, the aeroplane will have a mass which will allow it to land at the airfield. The way to simplify the dispatch rule is always consider the greatest mass in still air and the greatest mass in the forecast wind conditions. And of the two, take the lesser mass as the dispatch mass. Of the two, it is the still air mass that is usually the lesser mass, as shown in our example. The exception is when there is a tailwind on a unidirectional runway. A unidirectional runway is a runway whose direction for takeoff and landing is fixed in one direction. And in this case, the maximum landing mass in the tailwind will be less than the maximum landing mass in still air. Before we finish this lesson, let us work through the landing graph in CAP 698, which is on page 46 of section 4. As with all graphs, before you use them, look around the graph for any associated conditions or assumptions, and identify any correction information. In this case, there is a correction for manual spoilers, since the graph assumes auto spoiler deployment. To start our example, let us assume a landing distance available of 2,400 meters. Therefore, move upwards from 2,400 meters until the reference line for wind. For tailwinds, move down and left along the sloping guidelines, and for headwinds, move up and right. We'll assume a headwind of 20 knots, so move up and right along the sloping guideline until you reach 20 knots headwind. Then move straight up to the next reference line, which is for the runway condition. If the runway is dry, simply travel vertically upwards. However, if the runway is wet, which is what we will assume, travel up and left to this point. Then move up vertically to the next reference line, which is for the flap position. For flap settings of either 30 degrees or 15 degrees, move up and left along the guideline. But for 40 degrees flap, which is what we will assume, move straight up through the flap section until you reach the pressure altitude of the airfield, which in our example is 2,000 feet. From this point, move horizontally to the right and read off the field length limit landing mass. In our example, the field limit landing mass is 46,800 kilograms. Most Class A performance graphs, such as this one, already have all the necessary regulations and wet factors applied. Therefore, in this case, since it is an example graph for a Boeing 737, the landing mass of 46,800 kilograms ensures that the aeroplane will be able to achieve a full-stop landing within 60% of the landing distance available. Exceeding this mass will mean that the aeroplane cannot meet the landing distance requirements. However, there were other requirements that the aeroplane had to meet. Remember that the aeroplane must also ensure it can meet the landing climb requirements. From an example we went through earlier, let's assume the landing climb limit mass is 61,800 kilograms. There is one more mass to consider. The structural limit landing mass of the 737-400 series is 54,900 kilograms. Exceeding this mass may structurally damage the aeroplane during the landing procedure. Therefore, the maximum landing mass for our example must be the lowest of the listed masses, and in this case is 46,800 kilograms. This completes the lesson on the Class A performance requirements for the landing phase of flight. Make sure you are able to work out the aeroplane's landing distance and landing distance available using the factors we mentioned. These form a significant part of the exam. Also ensure you are very familiar with the landing graphs. And again, expect questions to test you on the use of these graphs. Make sure you dedicate a significant part of your time carefully going through questions in the period leading up to the exam.